Greetings everyone, I am Danish Rafiq from the Department of Electrical Engineering from NIT Srinagar, and I will be presenting my contributed paper which is titled as Structure Preserving Nonlinear Reduced Order Modeling Technique for Power Systems. Okay, so I'll begin with the problem setup first, then we'll talk about a little bit about the proposed scheme, then the case study that's involved in the study, and followed by some conclusions at the end. Okay, let's begin with the problem setup. Large-scale systems are becoming quite pervasive in all fields of engineering and applied sciences. And now the problem with large-scale systems is that they are very difficult to, or I can say they're very expensive to simulate and control. And one good example is a power system model. Now, as you all know, that worldwide power system models are becoming increasingly complex in size year by year due to the rapid growth of the widespread interconnects and much higher penetration of the distributed resources. And applications like transit analysis, security assessments, or trajectory sensitivity analysis is becoming highly combinatorial. So, due to the large scale nature, there's a need for reduced order modeling paradigm. So, this is the task of model order reduction, and researchers from the past have been studying this area and tackling problems encountered in large scale settings. Now, mathematically speaking, model order reduction can be framed as follows. The models arising in power systems are a set of differential algebraic systems given by this F and G, which are nonlinear mappings. Now the state vector X spans in the nth dimensional Euclidean space where the inputs are in M dimensions and Y is in P dimension. So this is essentially a MIMO system where the states can arise from the rotor angles or frequency, and the output is governed by the load angles. Now the problem is large scale in nature, which means and is quite large. What you want to do is you want to represent this system by a reduced order model in which the state vector x hat is reduced from n to r, where r is much less than n, and the inputs and outputs are same. This is the main aim of the MOR scheme, that is to keep the input-output relationship intact. Now here the goal is that the error between the output and the desired response should be less than some tolerance value for some admissible input signals, and the secondary goal can be to construct the approximation of the original state vector x from the x hat. Now there is a good motivation of using reduced order models. For example, in offline settings, reduced order models or ROMs are used for efficient numerical simulation, which means that ROMs solve in seconds versus hours. Also in optimization, in which we have to repeatedly solve a model for to tune a design to tune a optimization at hand. So what we do is ROMs are used for repeatedly solved instead of the full order models, and they are used for essentially those what if scenarios. Similarly, computer aided failure modes or FME analysis can be enhanced if ROMs are concerned. Also, in online applications like parameter estimation, uncertainty quantification, control, or predictive maintenance, recently digital twins are being used by ROMs. So ROMs basically facilitate the use instead of the full order models. Now, coming to power systems, the problem of MOR in power systems is known as dynamic equivalencing. Now, historically, methods were proposed that extract physical attributes of the systems, like coherency-based methods were proposed, or synchrony-based methods were proposed, or singular perturbation methods were proposed. Now there has been a shift. There was a shift basically, and the MOR community basically was interested to extract models or schemes that were based on mathematical properties instead of the physical ones. In these methods such as Krella subspace-based method or balanced truncation methods for power systems or measurement-based methods were initially proposed. Now, one of the reasons of the shift was that these methods they basically facilitated the use of renewable sources along with the power systems. Also, hybrid methods were also proposed, like heuristic optimization methods, artificial neural network methods, or independent component analysis by Arif et al. These methods was also saw a prominent success in MOR community for power systems. Now, what are the challenges introducing power system models? Essentially, power system models exhibit strong nonlinearities. This is due to the nature of the swing dynamics involved. Also, most of the MOR methods are based on linearization, which is that the power systems are divided into study area and external area, and the study area is preserved in detail, whereas the external area is basically linearized. And sometimes the linearization is not a faithful representation of the nonlinear system involved. So that's a challenge. Also, power system models are usually in second order structure, as I will show. So there's a high therefore the reduced order models are highly aimed to be that preserve the structure of the original system. Also, nonlinear MOR involves the reduction of only the state solution only. It's a famous problem in nonlinear community that the complexity of solving the nonlinear term f is spans as after the original dimension n. Now, usually the reduction is performed using projection, given a large scale system with the coefficient with the constants matrices m d, which are the mass and the damping matrices, and I'm having this nonlinear vector valued function f, which represents internal forces, and this input matrix b and an external force matrix f, and y is a output vector. Now here the dimension of the system is n. So this is a large scale system. What we do is basically we project the dynamics on a low dimensional manifold using the projection matrices V. By doing so, we basically reduce the number of unknowns in the system. Here the term RT comes, which is because due to the approximation of the linear mapping. So this essentially makes it an overdetermined system. To make it a well-posed problem, what we do, we enforce the Galerkin condition, which is we project on another subspace in which the residual term vanishes, and we finally get the Galerkin form. Now, the questions that arise is how do you compute the projection matrices V and W? This is where the different reduction schemes vary. Also, how do you preserve certain properties of the ROM? So coming to the proposed scheme that we have used, before I talk to the nonlinear moment matching, I will just introduce the linear moment matching. So if we talk about moment matching in linear mechanical systems, in which I'm having this stiffness matrix K, and I'm assuming that the system is asymptotically stable. So the idea of implicitly matching moments is well understood in linear community. Depending upon the damping of the system involved, I can extract my projection matrices using these Krylov subspaces, which are second order in nature for this condition. So this thing is very well understood, and this has been widely employed for a range of second order systems. Now there is a notion of time domain interpretation for moment matching. It was given by Astolfi and his papers. What the idea is that if you are using a linear second order system, which is known as a signal generator or an exogenous system, given by this phi dot, it's called capital phi, and its second derivative and the output. So there's a theorem that states that if it's assumed that this matrix P and Q are observable, then the ROM that we can extract match the steady state response of the full order system, which is well defined, and the projection matrix that we use to obtain the ROM is basically coming from a solution of a unique equation, which is known as the Sylvester equation, which is given over here. So a unique solution of this equation will give us the projection matrix used to obtain the reduced order model. Now this connection between the Sylvester equation and the Krylov subspaces was very well explored earlier. Pictorially, I can show you like this. If I'm having a system, the output of the signal generator is fed to the input of the full order system, then the movements characterize the steady state. This was the notion that was already being developed. Now coming to the nonlinear systems, if instead of a linear signal generator, I use a nonlinear signal generator now, a second order is nature. Now the mapping is from R to R is given by this pi matrix or pi mapping, and the output is given by this rho. So the idea is to use this nonlinear signal generator with a nonlinear second order system that we are interested to solve. Here the condition is that the nonlinear signal generator should be Poisson stable, which means every input that it generates should be persistently exciting in time. So if I use this kind of a signal generator with my nonlinear system, then the reduced order model, second order form, match the steady state response of the full order system, which is well defined again in this case. But the Sylvester equation turns out to be a nonlinear second order PDE, which we need to solve. And the solution gives us the projection mappings for which we will project our higher order system to the lower order. Pictorially, I can show you like this. If I've given a nonlinear second order signal generator that we can tune later on, the outputs generated by this signal generator can be fed to the second order full order model and the second order ROM. And the movements that I get give me the interpretation of the steady state matching. So the matching moments in this kind of notion is essentially matching the steady state responses of both the systems, and where this calligraphic P or PR are the solutions of the respective Sylvester equations. Now this kind of interpretation is quite useful for systems which doesn't have a transfer function model, or for nonlinear systems. So this kind of interpretation is quite useful for that. Now, the solution of in order to match the moment matching for nonlinear systems, I have to solve the Sylvester equation, which is quite expensive because it's a PDE and that too in second order form. So certain simplifications are proposed in the literature, like Maria et al. Have given some simplification, that is to use a linear projection instead of nonlinear mapping. Also to use the column wise consideration and time discretization. All these simplifications are inspired from POD, and using these simplifications we arrive at a numerical algorithm to implement. This algorithm extracts the projection matrix V for different signal generators. This is very easy to implement, and this avoids the expensive snapshot that are usually encountered in POD. Now, like I said before, that the reducing the nonlinear system using projection only involves the reduction of the state variables but not nonlinear function f. Therefore, what we have done is we have used DIME, which is a very famous method in MOR community, along with the moment matching, to get the desired ROM structure given as follows. Here the reduction is being performed of both the state variables and the nonlinear function f. Now, the case study involved is known as a ring grid model. It's having an AND generators identically connected with an infinite bus. The equation of motion is given as follows, and the nonlinear mapping is given by this electrical power demand. Here are the parameters that are used from Marik et al. His study. We have taken the parameters from his study. Here the number of alternators I have taken 1000, and the reduced order dimension is 15, and the DIME indices are just 50. So as you can see on the left, you can see a plot of the output responses. We have essentially taken 3 case studies. If I zoom here a bit, the first case study is when all the nodes start from under perturbation condition. The second case study is when all the nodes start from equilibrium point, and the third case study is when all the nodes start from over perturbation. The solid lines represent the full order models, and the reduced order model are represented by the dashed lines. As you can see that the full and the reduced order responses are indistinguishable from one another. On the right, you can see the error response. Again, the error is very appreciable. It's quite low. Now, quantitatively, you can see that the full order model is taking around 103 seconds to run on a Windows machine, and for the POD, which is a very famous technique for nonlinear systems, the reduction time is 109 seconds, and the online time is 33 seconds, totaling of 143 seconds. And our approach is so an LMM DIME, it takes just 5.8 seconds for basis time and 20 seconds for online time. The overall CPU time is improved significantly with an appreciable errors. This is for test case 1. Similar results are obtained for other test cases as well. You can see the savings in basis time and the online time. Now, conclusion is that the nonlinear MOR is a very attractive and open field of research. A lot of work is being done, and there is a lot of scope for future also. And an LMM DIME is computationally less demanding than POD, and it preserves the structure of the FOM, which is good. The choice of signal generator used in the study depends on whether it excites the important dynamics of the system, where it constitutes the eigenfunctions of the underlying nonlinear system. Now, the code used in this study is available online, so can be reproduced. A future work can be to investigate the suitability of this proposed scheme to a more realistic power system models, like we have the IEEE standard models in which we have certain renewable sources attached, so that can be used. These are some selected references from the study, and I will just thank you very much. I will just take some questions now.